Okay, Calc PC Unit 2, Day 4. The warm-up is actually going to be from this point down the whole front of the page. You're just trying to write all the rules, the derivative rules that you can remember. So see if you can try and do as many as you can. Skip the ones you don't know. And then I'll come back and fill them in. So do that first, and then we'll come back up to the top. So try the warm-up, try all these rules, derivative rules. Pause it. Okay, this is product rule. So it's f times g prime plus g times f prime, or the other, whichever one you do first doesn't matter. And quotient rule does matter. It's low d high minus high d low all over low squared. And because it's subtraction, the order does matter. So remember, low d high minus.
I have my thing at 3 o'clock.
Okay, a little interruption. Sorry. Low d high minus high d low all over low squared. Okay, the chain rules when you have an inner function, so you take the derivative of the outer function first, leave the inside the same, and then you got to multiply by the derivative of what's inside afterwards. Power rule, it's going to be n times x to the n minus 1. We could write some of these sort of in like more of a u substitution form where we expect an inner function. So it'd be n times u to the n minus 1. And then, of course, you'd follow it up with the derivative of what's inside, the u dx. Derivative sine x is cosine x. Derivative cosine is negative sine. So all the cos have negative derivatives. Tangent is secant squared. Cotangent would be the same as tangent, but cosecant squared, which kind of makes sense, but also a negative because of the cos. Secant is secant tan. And then cosecant is cosecant cotan. So I kind of remember these as pairs, but of course there's a negative there. No surprise. E to the x is e to the x. E to the u would be e to the u du dx. B to the x would be b to the x times the natural log of the base. So this is a special version of that rule. So b to the u would be b to the u, natural log of the base, which is just a constant, and then a du dx. Natural log is 1 over x, 1 over what's inside, or 1 over u, du dx. Log base b is 1 over x, just like this, but then it has an extra natural log of the base in the bottom. 1 over u, natural log of the base, du dx if it has an inner function. So this is just illustrating our common situation of inner functions and having to use chain rule. Inverse tangent, or arctan, is 1 over 1 plus u squared du dx if there's an inner function, which there often are. Inverse sine is 1 over the square root of 1 minus u squared du dx. And cosine is the same thing, but no surprise, there's a negative. So those are all those derivative rules that you guys should know. So that's the warm-up. You need to remember all these rules again. Now up here, we'll talk about the derivative as a function. So it is if you take a graph and you're like, well, I want the derivative here at x, and so that'd be the slope of the tangent line, but you need 2 points to find the slope. So one sort of solution is to go to the right distance of h, and then the coordinates of this point would be x, fx, and the coordinates of this point would be x plus h, f x plus h, and then you could find the slope of that line, which is a secant line, which we use as an approximation for the slope of a tangent line. So the slope of that line would be f x plus h, minus fx, rise, change in y, over run, h, which comes from x plus h minus x. And what we do is if we make these closer and closer to each other, they get closer and closer to the actual value. And if we take the limit as h goes to 0, make them infinitesimally close, then you get the actual definition of the derivative. Okay, so this is the definition of the derivative. There are other versions. Instead of a point to the right, you could use a point to the left at x minus h, fx minus h, and then it would be written like this as h approaches 0 of f of x minus f of x minus h all over x minus x minus h, and you would get positive h. You could do a symmetric version where you do a point to the right and a point to the left, so it'd be fx plus h minus fx minus h all over 2 h's would be the difference, the run. But there's even other ways we could write it. If you have 2 points, x1, x2, and call the difference between them delta x. So you might see, well, the limit as x1 approaches x2 of f of x2 minus f of x1 all over x2 minus x1. So it could be a different way of writing it, or the limit as delta x approaches 0 of delta y over delta x, which starts to get into kind of some of the form we write dy dx kind of means that small change in y over small change in x. So there's a lot of different ways. Now, when you see a limit, we deal with lots of limits like we have been, but sometimes they look very suspicious, like, hey, this is a derivative, okay? And if you recognize that it looks like a derivative, one of the versions of derivatives, then the quick way is to be like, okay, well, what's the function we're trying to take derivative of? X cubed, it shows it twice there, right? And then you say, well, let's just find the derivative using the rules that we memorized, 3x squared. And sure enough, the answer to this is 3x squared. So that's something that's good to take advantage of. Otherwise, you could just sometimes, I mean, you could do L'Hopital's rule and stuff like that we haven't even talked about again yet. But sometimes they have a number where the x goes, and it's still the derivative, but what it's saying is it's looking for the derivative at 3. That's what we're trying to find. So you'd say, okay, well, what's the function x cubed? What's the derivative in general? 3x squared. And then you would plug 3 into it, and you would get 27. So sometimes they look like that. Okay, on to the back. So back, I have a couple just other kind of unique sort of derivatives that you could just do some different tricks. So implicit differentiation is when you can't solve for y by itself, or it's hard. You either can't solve for y, or it's hard to solve for y. And if you can't, then you can't differentiate explicitly. So explicitly is the way we usually do it. So what we could do is we could just start taking the derivative as it is, 3y squared. But y is a function of x. Even if you can't get it there is a version of it. And so there's a y would be like an inner function with a bunch of x stuff. So we still got to follow it up with the derivative of what's inside. That's a chain rule idea. But instead of trying to get it in terms of x, we just write this. That's the derivative of the inside. Plus cosine of xy. But then we got to take derivative of the inside now. The derivative of the inside is going to involve product rule, so you better use parentheses. X times derivative of y is dy dx. plus y times derivative of x with respect to x is 1 equals derivative of x on the right side is 1. So we've taken the derivative. Now we got to try and get the dy dx by itself, which is kind of a little messy algebraically. But we could do it. So maybe the first thing to do is to kind of break things up, distribute this x cosine xy dy dx plus y cosine xy equals 1. And then what we could do is we could group the dy dx terms together and factor the dy dx out, because that's kind of the trick when we can't combine their coefficients because they're not like terms. So you get 3y squared plus x cosine xy. Our goal is to get dy dx by itself. Move that guy to the other side by subtracting it. Okay, and then we could just divide, both sides by this, and so then we get dy dx equals 1 minus y cosine xy over 3y squared plus x cosine xy. Now the answers to this is implicit. The answers to implicit differentiation usually have y's in them. Otherwise, your y was probably already by itself. Log differentiation is a way of using logs. If they're there, you can use this, but if they're not there, we can introduce it. And so it's to use log rules to break up crazy expression. So if you take the log or the natural log of both sides first, now whatever you do to one side, you got to do to the other side. So if there's already a natural log there or log, then it's going to make it easier. Now I'm going to go with natural log because I see an e in there, and I think that might benefit me a little bit at some point. So I'm taking the natural log of both sides. So then I'm going to take the derivative implicitly. This problem didn't need to be implicit to begin with, but if I'm using this technique, I'm going to have to take the derivative of natural log of y, which is 1 over y, dy dx. Now the right side's going to all be explicit, but what we're going to do, actually before we even get there, is break this up using log rules. So we could break this up into two separate logs by doing subtraction, right? And then we could break this one up into two separate logs with addition. And one thing we could also do is move the powers inside and front as coefficients. That gets rid of a couple extra steps. So over here, you're going to want to think of this as parentheses e to the x plus x to the 1/2. And then we can move that out in front. We can move that out in front. So this is all just algebra breaking this down. 3 natural log of x plus natural log of sine x minus 1/2 natural log of e to the x plus x. I think that's as much as we can do. But now we're going to take the derivative implicitly. And so that's going to be 1 over y dy dx. And that's really the main implicit step is over here on the left-hand side. And then over here, we're going to get 3 over x plus 1 over sine x. But then you got to take a derivative of what's inside. So that's going to be cosine x minus 1/2. 1 over everything that's inside. But then we got to multiply by the derivative of what's inside. Chain rule, e to the x plus 1. And this is what we want to get by itself. Now, this is kind of messy. We could do some things to clean it up. We could say, this is 3 over x. Cosine over sine is cotangent x minus e to the x plus 1 over 2e to the x plus 2x. And then if you want to get the dy dx by itself, you're going to multiply both sides by y. But since this problem was originally not going to be implicit, we probably don't want the y in there. But we easily have the y, an expression for the y. So we're going to say x cubed sine x over the square root of e to the x plus x times parentheses 3 over x plus cotangent x minus e to the x plus 1 over 2e to the x plus 2x, something like that. It's pretty messy, but hey, we did it. But here's the deal. if you hadn't done this and you just took the derivative of this originally the way it would have been pretty gross. It would have been a quotient rule right away with product rules in it and lots of chain rules in it, and it would have gotten pretty gross and it would have been pretty hard too. So today's assignment will be these two worksheets. So 2-4. I think I might end up calling this 2-5, but I don't know. We'll see. But try these worksheets. You should be, I guess, I don't know, maybe happy that there's no more book work. It's been a while. So try those out.